formula sheet, you have some formulas for exponential equations. You have a compound interest formula, and you have a natural growth formula. I've heard that they're taking those formulas off, and then whenever they ask them on the final exam, they'll put the formula in the question. So it's not so bad. Because they want to add more formulas, and they don't want to fill up the formula sheet with like tons of formulas. So it allows them to give you any exponential formula in any situation. Even if you haven't seen the formula before, you should still be able to use it. Okay? So one of these formulas is compound interest. And here's the idea of how compound interest works. So we'll just go through this example. So you have $100, and it pays 2% interest compounded annually. So that's not very much, and it's not very often. Compounded annually means that at the end of the year is when they're going to figure out how much interest they're going to give you. If it was compounded monthly or compounded twice a year, they would figure out at the end of every month how much interest they would give you and pay you at the end of the month. So compounded annually doesn't happen very often. So at the end of the year, they say, well, 2% of 100 is $2, so we're going to give you an extra $2, and you're going to end up with $102. But what they want you to see here is that here's your $100, they add 2% more, which is $102, but instead of writing it as 102, they're going to show you that if I factor out of 100 out of both of these, I'm going to get 100 times 1 plus 0.02, which gives me 100 times 1.02. So with it factored out, it's 100 times 1.02. And you might have seen this before, like when you get charged a certain percentage, like GST. Right? You could take the amount, which is $8, and then add 13% of 8. Or you could just take 8 and multiply it by 1.13 and get the total amount right away. But what happens is with compound interest, if you follow this pattern through, you say, what happens at the end of 2 years? Well, after the first year, you have $102, which is this. This is your $102, 100 times 1.02. And then you get 2% of that. And what 2% of that is 2% or 0.02 of 100 times 1.02, which if you factor the 100 times 1.02 out of both of these, you're going to get 1 plus 0.02 again. And you get, now after 2 years, 100 times 1.02 squared. So you get an exponential equation that is y equals 100 times 1.02 to the x as how much money you have. This is a basic exponential graph. It will still have an asymptote. Since I did it in red, I'll make the asymptote in black at 0. Okay? It has a vertical stretch of 100. So instead of 0, 1, you have 0, 100, because that's how much money you started with. And then after 1 year, you plug in 1, you have 1, 102. So I should really put that really low there, because that's a slight increase. But it will have this shape. And eventually you will have lots of money, right? Unfortunately, before that graph at 2% interest is lots of money. There's another point on this graph. Death, you're dead, you don't get lots of money, you die way before that ever happens at 2% interest. But if you want to set a legacy for your great-great-grandchildren, maybe you could invest some money. And after you die, and they die and die and die and die, someone down the road will have like $1 million. And at that time, you can take $1 million and go to a pop machine and buy a Coke because of inflation. So maybe it's not the greatest idea to invest at 2% interest. But if you had a higher percent interest, it could be very, very good. So this pattern keeps going, and you get your compound interest. Now, what happens is what if you are compounded more often? So now here it's twice a year. What happens when you do twice a year? And basically the way that interest works is if this 2% was compounded twice a year, they'd say, well, normally for a whole year, you would get $2. So halfway through the year, we'll give you half of that. So halfway through the year, they give you your first dollar. But then on the second half of the year, you would get your second dollar plus 2% of your first dollar. So you would get an extra 2 cents if they compounded it twice a year as compared to once a year. And the idea is if it's compounded more often, you'll get a little bit tiny more each year. But it doesn't amount to a lot. So this is one thing as far as if you would take one thing from this unit later on in life for figuring out things. The number of compounding periods does affect it, but it doesn't affect it a lot. What will affect it a lot is the percentage of the interest. Now this will come in more important when you are actually borrowing a lot of money. Okay? Sometime in the next 10 to 15 years, some of you may buy a house. And when you buy a house, you may borrow $200,000, $300,000, $400,000 from a bank. Then you're going to be wanting to make sure you find an interest rate that's as low as possible. Because even a 0.25% changing from 3.25 down to 3 might save you tens of thousands of dollars over time. And we can look at some examples with our graphing calculators to see that later. So what ends up happening is we have this compound interest formula. On your formula sheet before, it was written like this. Amount, instead of A with a little 0, some places you'll see that as a P for principal, and principal is the amount that you started with. 1 plus, sometimes it's an R instead of an I. The I stands for your interest rate. Sometimes they have R for rate instead of I. N is how many compounding periods per year, and T is time. So you have your principal, the amount of money you're starting with, and then because your rate has to be divided by how many compounding periods, because like I said, with it compounded twice a year, instead of getting the $2, you're getting only half of that. And then that also affects how much goes in the exponent, because your time is based on how many compounding periods as well. Oops. Go back here. And this formula is sometimes rearranged because these inside the brackets here are all numbers that you know. So if you added them together, if you went 1 plus and you took the rate and you took the compounding periods and got a number, then this could just be written as K, and that's where they get this formula from. It's the same idea for exponential growth. And because a lot of things like populations almost grow continuously, on your formula sheet right now, there is a formula for continuous growth. And continuous growth has a principal amount, and the number E appears. T is still time, R is still a rate, but if something is growing continuously at a rate of 2%, then the formula all of a sudden has an E involved in it. So here's example 1. So first of all, we're going to have to know what some English words means. How often is quarterly? How many times a year? Every 3 months, which is how many times a year? 4 times a year. So that's going to tell you that your N value is going to be 4. So we got $1,500. We want to find out what the amount, when will the amount be $2,500? So here's the formula. I'll use the way it is on your formula sheet. Again, on your final exam this year, this formula would be given to you in the question and everything labeled for what it means.
Wait, really?
Because they could give you any formula, so to be fair, they would have to tell you what things are. I don't know if some of them they'll assume that you know some things, because this is the first, this exam coming up will be some of the first ones where they do that, where they put a formula on. Some of them they will explain things. I haven't found out if there's some like this one they're going to say, oh, we assume you know this. But I don't think so. I think they'll put what everything stands for. So we want to know the amount is $2,500. The principal is $1,500. The rate is 4%, and you change that to a decimal, 0.04. It's quarterly, so we divide by 4. And what we want to solve for is t. Now in 5.2, we solved for exponents by trying to get both sides to have the same value. Trying to get both to have the same basis. I can tell you right now, just by looking at the numbers, none of these are going to be on our powers chart. This is not going to work very well. So we're going to use the same strategy that Jack did at the beginning, where he graphed both on both sides and then said, where do they intersect? So we're going to take out our graphing calculator for this, because we don't know how to solve for exponents otherwise yet. We're going to learn that later when we learn about logarithms. But for right now, I'm going to take out our graphing calculator. I'm going to put this side into y1 and this side into y2. As a basic idea, this is a straight line, so somewhere, just a quick sketch, 2,500 is going to be a straight line. And somewhere over here, I'm going to have an exponential graph with an initial point of 0, 1,500. And because this value is bigger than 1, I know that it's increasing, and somewhere they're going to intersect. Most likely, if after you type these things in, now careful when you put two things into an exponent, if you don't put brackets, your calculator will think only the first number is in the exponent and the second one isn't. Some of the new calculators automatically build it up there and show you that you're typing it up there, then you wouldn't have to worry about brackets. But I'll need to put brackets in here. Now, chances are when I graph this, I won't see anything because my window isn't set up. That's why the sketch that we did over here is so important. You know that it's going to be starting at, the one graph starts at 0, 1,500. The other one is a straight line at 2,500. So when I go to my window for my y values, I don't need to see negative 10,000. Probably negative 10 would be fine, or negative 1 is probably going to be good enough. And I need to see past 2,500, so I'm just going to go up to 3,000. I'm going to see if that changes anything for my graph. There's my 2,500, and sure enough, there's my graph going up. And I happen to have my x scale okay. I think I still had it from the previous question where we went to 30. My x scale is okay, and they show they intersect. If you see part of your graph but not see the intersect, you're going to have to change your x window so that you can see all of it. And now I can calculate the intersection. Push enter 3 times, 2, 3. And my time is 12.83 years. So the questions you can do for this one are 12 and 13. Example 4 is very similar to this. I'll tell you after example 4, the only difference between example 3 and example 4 is that they're talking about decay, which means that this number inside the brackets is going to be less than 1. So your graph would be going down instead of up. But you would still find the intersection the exact same way. So I'll let you do example 4 on your own, and you can do question 14 as a result of that one. But I'll tell you a story about question 4 while we last couple minutes.